Like I mentioned in that warm-up, that very last question asked you to decide whether that represented a linear function, and John gave us a good response there. Basically, a linear function has a constant rate of change. Linear function has a constant rate of change. And again, rate of change, when we say that, we're basically talking about what? Slope. Slope, okay? Rate of change, slope. We know a linear function has slope. That slope is the same regardless of the portion of your graph you're looking at, okay? And what is the graph of a linear function? Line. All right, grab your calculators because I think we're gonna do a couple of these graphs on our calculators versus by hand, just to kind of expedite our process a little bit. First example, the town of Noblesville has a population of around 54,000 people and grows by 2,300 people per year. Since population P is growing at a constant rate right there, it tells you right away we're looking for a linear function. You see constant rate, you know it's a linear relationship. That population P is a linear function of time T in years. Okay. What is the average rate of change of P over every time interval? So you are given this function here as a verbal description. So you only have two values here. Which of those describes our average rate of change? The 2,300, the amount by which our population grows per year. Okay. All right, so then we are going to turn our verbal description into a table. And it says to make the table looking at the population every 5 years over a 20-year period. So we'll look at when T is 5, 10, 15, and 20. Let me ask you this. When T is 0, what's the population? When T is 0, what's the population? Okay, I need more than like 3 people to participate in class. Kyle. 54,000. Okay, that 54,000 is our population at T equals 0. Okay, thinking about that now, how are we going to calculate our population after 5 years? Spencer, right? Yeah. Okay. Very good. So we're going to take that growth per year, multiply it by 5, and then add it to our initial. And we should be getting 65,500. Take about a minute. I want you to find the next 3 populations. Zach, when T is 10, what's our population? Okay, 77,000. Robert, when T is 15? Okay, and then finally when T is 20, we should hit a nice 100,000. Okay. All right, we are working through every representation of our function. We were given the verbal, we went to the table, now we're actually going to write the formula for our population. So our population is equal to our initial plus, like Kyle said, we grow 2,300 people per unit of T. Okay, so instead of graphing this by hand, which I'm going to assume that you guys know how to plot some points and get a line, let's just graph it on our calculators to see what this looks like. Even though our formula that we wrote is T in your calculator, you're still going to use that X. Okay. So we've talked about this before. If you're just on your standard viewing window, we are not going to see this graph at all because the y-intercept is much above, where we're working. One thing that you might try, if you go to Zoom, and I think it's 0 maybe. Yeah. Okay. Option 0 is Zoom Fit. Sometimes this works well, sometimes it doesn't, but it's worth trying. Basically what it will do is automatically adjust your window to fit your graph. So here it's working pretty well. You can see that y-intercept, and then we can see that this is definitely a linear equation. We have that straight line graph. Okay. Are we good? All right, let's move on then. I'll get this example started for you, and then I'm going to have you guys kind of finish it off. It says a small business spends $10,000 on a new phone system and for tax purposes chooses to depreciate it to $0 at a constant rate over a 5-year period. Make a table and graph showing the value of the equipment over the 5-year period. Now, split that one in half because you don't have enough places in that table. So essentially what we're looking at is from when T is 0 all the way through, oh, we're really missing some. Shoot. You're going to have to split a couple in half. Through when T is 5, the value of that equipment each year. Now, what we have to think about for a minute is this. It starts at a value of $10,000. So when we get this equipment right away, its value is that initial $10,000. And then it depreciates after 5 years to 0. So that's what we know. What we have to figure out, which is not explicitly told, is how much it depreciates per year. Okay? Now we know it's depreciating at a constant rate. So with your table, take a couple of minutes to think about this and find those values for when T is 1, 2, 3, and 4. Go. Blake's down there too?
Yeah, but she's for Bruin during this month.
Oh, and he's down there, yeah.
Yeah, he doesn't have a class, so. They said they're both in a regular amount.
Oh,
She had all your papers.
good. Okay, I'm gonna pick on Robert because I overheard some things that he was saying to his group that I would like for him to repeat to the whole class. So Robert, I want you to kind of repeat what you were just saying about, about how you figured this out. Go, nice and loud.
You can do the formula thing.
Okay, what formula thing? We're in pre-cal.
Okay, the function, the slope thing, the functions.
All right, keep going.
Name. It's the function over the numbers.
Okay, the function
What
value.
you've been doing.
Average rate of change. You said it to your group.
There you go.
Okay.
Average rate of change.
Okay.
And then you get the slope, and then you just subtract by that.
Okay, so, what did you get for your average rate of change?
Negative 2,000.
Negative 2,000. I know probably some other groups look at it a little bit differently. If you just divide that 10,000 by 5, you get a positive 2,000. Then you just need to realize that you're subtracting that every time, okay? So we should have 8,000 and then so on. All right. Part B, write a formula for value V as a function of time. Okay, 90 seconds with your table to do this part as well. Go. Is it already? All right. Trevor, what did your group get for your formula? Awesome. Anybody have anything different? Questions? Okay. And again, let's just go ahead, graph that on our calculator as opposed to taking the time it would to do that by hand. Okay. So you'll have to maybe use Zoom Fit again so that your calculator adjusts your window to get this to show up. Okay. So we can see, that initial value, and then over 5 years it depreciates to the 0. What questions or comments do you have so far? Okay, let's kind of go back, look look at what we're doing here. So it says to rewrite the formulas from the last two examples using the symbols X for input, Y for output, and B initial value and M rate of change. So just replacing X and Y for T, and I don't remember what else we used. T. And then replacing the V and the T with X and Y as well. We can see our value of B in that first one would be the 54,000. Our value of N would be the 2,300. Similar thing over here. Value of B is 10,000, and then N would be negative 2,000 in the second one. In general, what I want you to be noticing is that in these situations, we have that the output, or Y, is equal to our initial value. That initial value is essentially your y-intercept, and then plus the rate of change times the input. Okay? Our linear functions are going to follow kind of that general form. So if y equals f of x, if that is a linear function, then in general, y equals b plus mx. Your initial value plus the rate of change times your input. That value of b, your y-intercept, I want you to start thinking about this as your initial value when t equals 0. You're not going to be just given random equations to graph anymore. You're going to be given formulas that represent situations. Okay? So we really have to understand what these values mean in the context of what we're talking about. And then that slope is essentially our rate of change. I always like to make the note, you guys are used to seeing linear functions as y equals mx plus b, right? So you can see that this kind of imposes the y-intercept and the term mx. And the reason for that, again, is because we're talking about this in the context of a situation. It makes more sense if we talk about that initial value where we start when t is 0 and then add in the rate of change. Now, with that being said, if you write it y equals mx plus b, no, I'm not going to take off, but just understand why it's different here. Okay? Yeah? All right. Kind of like in your warm-up, you had that table and were asked if it was a linear function. We can kind of see now how we'll do that, looking at the rate of change. We've already mentioned this, but if the rate of change is constant for all pairs of points, that's important. All pairs of points in the table, then it's going to be a linear function. So if your change in output over your change in input is constant, then you have a linear function. All right, so looking at our first table, kind of thinking back about what John said earlier. Looking at our table of values, we actually have two different functions here, P and Q. Could either of these functions be linear? So let's focus on P of X first. Notice that your input values are increasing by the same amount. That's important. Look at your output values. Are these increasing by the same amount? Yes or no? Yes, okay? So because input is changing by the same, output is changing by the same, we can say P of X is linear. What about Q of X? So now looking at these output values, we increase by an amount, we increase by another amount. So looking just from the first to the second, we increase by what, 4 thousandths? And then here, we're moving up how much? Right. So because those output values are not increasing at a constant rate, Q of X is not linear. I said it's important to note that those X values are increasing by the same amount. That's not always going to be the case. If you look at the next example, it says it's possible to have data from a linear function in which neither the X or Y values go up by equal steps. But again, it is the rate of change that needs to be constant. So the former Republic of Yugoslavia began exporting cars called Yugos in 1985. Our table gives the quantity of the cars and the price from 1985 to 1988. All right, so example A says explain why Q could be a linear function of P. So P is our input. Let's make sure, again, we understand that. This is our input. Q is our output. If you look at your input, you're increasing by, what, 20, and then 90, and then 130. So your input values are not increasing at the same rate, nor are these values. But that is not what matters. It is the rate of change that matters. So what we have to do is look at the rate of change between each of these pairs of points. Yes, 3 times. Okay, so let's do that. So starting with these first 2 points, taking the difference in my output over the difference in my input. Have your calculators handy. So once we calculate that, we get an average rate of change of negative 50. We are going to do the same thing, like I said, between the two other pairs of points. So now I'm looking at the 43,000, 38,500 as my output. Finish calculating that, and then I also want you to calculate that last rate of change for the last two pairs of points, okay? Take a couple of minutes to do that. All right, you guys are looking pretty good here. So what we should be seeing is that even though our input and output are not increasing by the same amount, the rate of change is constant, okay? Now, the question that we have next, what does this rate of change of negative 50 tell you about these cars? What does that negative 50 mean in this problem? Talk with your table for a minute. What do you think? Libby, what did you guys say up there? Okay, that's a really good start. So, the number, I'm not sure exactly how you phrased this, so forgive me if it's not exact. The number of Yugos decreases by 50. Now, it's not every year. Why not? Because time is not our input, exactly. Price is our input. So the number of Yugos decreased by 50 when what happened? Yes. When the price increases by $1. Good. Questions, comments? All right, babes, we got one last thing to talk about here. It's a warning. Heed my warning. Not all graphs that look like lines are linear functions. gives you an example. P equals 200 times 1.02 to the t. Models the growth of a new type of bacteria. P is a population, T is the number of hours after the initial hour. Let's make a table for the first 6 hours of growth, and then we are actually going to graph this one by hand, okay? So we're looking 6 hours, so 0 up to 6. And then we can use that formula, plug in each of our values of t to find our output. So for example, and make sure you're using order of operations, so exponent first, 1.02 to the 0, and then multiplying that by 200. That initial population is 200. And then doing the same thing, plugging in the other t values. So take a moment for yourself to do that. And you can round to the 100th if you want. Oops. Double check that you have the right values there. And then let's go ahead. We are going to, what did I do? 1, 2, 3. Every third little box will be 1. Let's set up our axes here. And then we can make our y-axis go from 200 to like 230 maybe. And then it's just a matter of plotting those points whenever you get to that point.